Entanglement and excitons can be understood as two complementary ways quantum correlations move through the universe. Entanglement primarily uses light to distribute correlations across space, while excitons use mass-bound quasiparticles to move correlations through matter. Together, they form a single framework for how quantum information propagates, differing only in the medium that carries it. Photons are best suited for space, excitons for material systems, and they are not competing mechanisms but complementary ones. At its cleanest, quantum entanglement manifests through light. Photons are massless, travel at the speed of light, preserve quantum coherence over long distances, and interact only weakly with their environment, making them ideal carriers of entanglement across space. When two photons are entangled, measuring one instantly constrains the state of the other. No energy, mass, or signal travels between them. Only correlation exists, encoded in a shared quantum state defined at their creation. This is why quantum teleportation relies on photons, why quantum networks use optical fiber or free space links, and why entanglement can span kilometers without meaningful degradation. Light does not transport matter or force in this context. It carries correlation across distance. Excitons represent the opposite regime. An exciton is a quasiparticle with effective mass, created when an excited electron leaves behind a positively charged hole, and the two remain bound by Coulomb attraction. Unlike photons, excitons exist only inside materials. They carry energy, momentum, and spin, and they move by hopping through atomic lattices rather than propagating freely through space. In this sense, excitons are mass-based carriers of quantum organization. They enable energy transfer without charge flow, allow information transport with very low heat dissipation, and provide a natural bridge between optical signals and electronic systems. If photons move correlations between places, excitons move correlations within structures. Spin is the unifying bridge between these two domains. Magnetism is simply organized electron spin. Excitons inherit spin from their constituent electrons. Photons encode spin as polarization, and entanglement links spin states across distance. Through spin-orbit coupling, a particle's motion becomes tied to its spin orientation, allowing geometry to guide particles, magnetic textures to steer currents, and lattice structures to encode information. This is why phenomena such as chiral magnets, unusual Hall effects, and excitonic control converge conceptually. They are all spin-guided information systems. Viewed cleanly, space and matter separate into distinct but related roles. In space, photons carry correlation and phase without mass. In matter, excitons carry energy and spin, often without net charge transport. Magnetism reflects spin alignment without large-scale particle motion, while entanglement represents the distribution of quantum state itself without signals or forces.